Hello everyone, welcome back to our NPTEL course on scanning electron ion probe microscopy in material characterization. In last couple of classes, we have been discussing on gas field ionization source and its properties and how the ion source or ion beam is condensed to a very finer spots using an ion optical column. In the ion optical column, we have seen that we use only electrostatic lens, unlike the electromagnetic lens used in scanning electron microscope. In today's lecture, we will be particularly focusing on ion solid interaction, that is nothing but ion matter interaction and the signal generation, particularly effect of ion mass, generation of different type of signals including ion induced secondary electrons and the backscattered ions. These we will discuss, and also we will discuss on the mechanism of ion induced secondary electron generation when helium ions interacts with the specimen or sample. This is what the schematic diagram in our helium ion microscope. At the top we have gun, and then we have extractor to ionize the gas atom, that is helium and any other gases, so we pass into the column, and then extractor is given a negative potential to pull out the ions from the tip or apex of the gun and brought it downwards, and once the ion beam comes downwards, it has to be condensed using condenser lens, and using the beam alignment we focus into the objective lens. Through it passes through its aperture, beam limiting aperture, and using the deflector we scan the ion beam onto the specimen surface, and the objective lens used for focusing the ion beam onto the specimen. So, once ion beam incident on the specimen, how it interacts. First things that the beam range, this we have discussed earlier. The beam range has a important factors in the signal generation. As we see here, the ion beam range, or nothing but the range to which it go inside the specimen, that is the beam range, is smaller in case of hydrogen helium ions. Even it is further smaller with a bigger mass ions as compared to the electrons, which certainly have a larger beam range. It can penetrate much deeper into the specimen as compared to the ions. As it can penetrate much deeper into the specimen, it can interact with more number of atoms into the specimen, and therefore, signals will be generated from a larger volume of the specimen. As signals will be generated from a larger volume, certainly the resolution will accordingly be deteriorated. And here we see that certainly as we increase the acceleration voltage, the beam range is increases, because by increasing the acceleration voltage, energy of the incident particle ions or electrons increases, therefore, they can go much deeper into the specimen. Moreover, this beam range is inversely related to the density of the specimen. So, as per the Kanaya-Okayama expression, the beam range is related to the density in addition to the energy of the incident beam. K is a constant and P is also a constant. So, this we have discussed earlier. Similar in the similar line, what we could see that the interaction volume for the ion beams is different as compared to the electrons. If we consider about different type of ions, then here we have different type of ions that have been used in gas field ionization source for microscopy purpose or for other purpose, including like nanofabrication, lithography purpose, or for damaging the sample. These application patterning the sample, different type of ions are used, but for the microscopy purpose we use helium ions certainly it has to be inert, otherwise if we use hydrogen, hydrogen have also been used for microscopy purpose, but it is not suitable for all, it cannot be used for all kind of sample, because hydrogen produce a reducing atmosphere and it can react with the specimen. Therefore, helium being inert is preferred for microscopy purpose. Now, if we see the interaction of ion matter, then certainly once the ion beams incident on the specimen, they go in the forward direction, and once they go in the forward direction, then it starts to go in the lateral direction certainly, and producing the signal. Now, once electron also has same, but electron penetrate more deeper because it has a larger beam range. Similarly, helium also penetrate deeper into the specimen, and then it started to go in the lateral direction in increasing the volume of the interaction, increasing the interaction volume. But remember that whatever the signals generated here, particularly for example secondary electrons, but which is used for the microscopy purpose, that cannot reach the specimen, that cannot reach in the specimen, they would be self absorbed inside the specimen. Only the electrons near the surface will be emerged, and that can be used for microscopy purpose, because secondary electrons have energy very low, less than 50 electron volts. So, whatever the secondary electrons etc. are generated in this interaction volume, they cannot reach to the specimen and cannot come out of the specimen. Therefore, they will not be utilized for our imaging or other purpose. What another important factor we can notice from this figure is that compared to the helium, as you see the neon, interaction volume is again less, interaction depth is less. This lateral direction will be more and more as we go increasing the mass, but the beam range, the depth will be certainly less. You see the scale here 80 nanometer, in the on the other hand it is 250 nanometer here. Moreover, if we look carefully here, this region is more wider. This region become more wider as we increase the mass of the ion, and if the this region is wider, that means the signals is coming from a larger area of the specimen, resolution will be poor. So, therefore, argon, gallium, neon etc. are not very suitable for high resolution microscopy purpose, but because these ions have a higher mass, they have a higher momentum, they can sputter away the specimen atoms from the surface. Therefore, they can be they are best suitable for nano fabrication purpose or for damaging purpose. Gallium is more extensively used in nano fabrication in dual beam scanning electron microscope. In addition to that, as you see, it is written here, for electrons the interaction volume scale increases with beam energy E as about e to the power 1.6. So, interaction volume increases certainly with energy of the electrons, which changes as we change the acceleration voltage to a power of e to the power 1.6. On the other hand, ions, it is only proportional to the e to the power 0.6, much smaller. So, even though we increase the acceleration voltage, interaction volume do not increase as significantly as compared to as that of electrons for the ions. Therefore, ions when interact with this specimen, the signal comes more from the surface or near the surface. That it can give more surface information as compared to the electrons when we use as a source. So, if we again compare, let us say these are the comparison for different interaction volume with different ions in molybdenum. This was for molybdenum sample, this is at 40 kilovolt acceleration energy. But if we compare between the electrons and ions in a single slides, then we can see here helium ion beams which has a energy of 30 kilo electron volts. Once it is incident on the surface, as you see, they are going in the forward direction, much forward direction. As compared to the gallium with the same acceleration voltage, it has much lesser, because it has larger mass. It cannot penetrate much depth, its velocity will comes down as quickly with that same energy, velocity will be less, but it has a much greater lateral direction as compared to the helium. And here also we see that this region where electron beam interacts, that is much that means ion beam interacted, that is much wider as compared to the helium. So, certainly gallium is not suitable for high resolution microscopy purpose. It has much of the recoil effects. Gallium will recoil with other atoms and it will keep on moving in here and there in the lateral direction more and producing the signals from a larger area. And the third things, if we look at the electrons, if you see the electrons, now electron beam energy is only 1 keV, because it is small mass, we do not need to have that high acceleration voltage. Still it can going certainly downwards, less deeper, but again this area, the surface at which it reacts, this area is quite larger compared to the helium here, even at 1 keV. Even if we go at higher acceleration voltage with the electrons, certainly they will go much deeper and producing a larger interaction volume. So, what if we want to sputter away the material from the surface, then one can choose heavier ions, and that is what is being chosen for practical application using gallium ions as compared to other lighter mass ions. But for the microscopy purpose, helium is the most suitable ions because of its inertness and also not very large mass. Therefore, it can gives the better resolution in for the purpose of microscopy. If we discuss about the signal generation, then we know in scanning electron microscope we have secondary electrons generated from the surface of this specimen, and we have backscattered electrons that have more energy greater than 50 electron volts. These are the two primary signals generated which are used for microscopy purpose in our scanning electron microscope. Here again we say secondary electrons are emitted, and those secondary electrons are designated with IESI. Those secondary electrons are generated with the IESI, that means ion induced secondary electrons, as compared to the secondary electrons we normally designate when electrons is bombarded, when electron is incident on the specimen, and then primary electrons is incidenting, on the specimen, and the electrons generated on the specimen we say secondary electrons. But on the other hand, if it is the primary ions, the incident ion, primary ion incidenting on the specimen, and then secondary electrons are generated on the specimen, then we are designating as ISI. Now, this ISI and SE both have energy same less than 50 eV. If any of these electrons coming from this specimen have energy less than 50 electron volt, by definition wise we can say them secondary electrons. Now, whether they are same, actually energy wise they are same, but the process they are emerged and the information they provide will not be same. They are identical, but not exactly same. Now, first thing we talk about, let us say SC and ISC, what difference is that between them. When an electrons is incidenting on this specimen, from the same place an electrons come out with energy less than 50 electron volt, we term it as SE1. Certainly electrons will penetrate more deeper into the specimen, from all the area secondary electrons will be generated, but they cannot reach to the specimen and cannot come out. So, therefore, they are meaningless, they will self absorbed inside the specimen, but some of the electrons will recoil back who have those having energy little higher, and they will come out of the specimen. And if these electrons have an energy greater than 50 electron volt, we say it is a back scattered electron, BSc. That is what we have discussed in our scanning electron microscopy part. Remember that we say it back scattered electron when the energy is greater than 50 electron volt, and when a back scattered electron comes out after going through the specimen, then while it comes out, certainly it has lose its lot of energy inside upon interacting with the interaction volume, its energy become less. When energy of the incident beam is less, more number of secondary electrons are generated. So, here also some secondary electrons will be generated, these are designated as Sc2. So, now you see this Sc2 also have energy less than 50 electron volt, that is why we are saying secondary electron. Now, more Sc2 are generated because the incident electrons which will lose its energy upon interacting with the materials, and while coming out it could produce more Sc2 because its energy become less. So, if the incident energy, this incident energy is less, then we will have a more secondary electron 1 emerged from the specimen. Therefore, for high resolution microscopy, we prefer not to use high energy electron beam. We prefer to use a low acceleration voltage, particularly in the range of 2 to 5 keV. This is good enough to get good enough to maximize the secondary electron 1 yield from the specimen. So, now even though that we have lot of Sc2 generated, but on the these are about Sc1 and Sc2, and in the scanning electron microscope or SEM, more secondary electron 2 is generated as compared to the Sc1, and therefore, secondary electrons, because of higher yield of Sc2, our resolution will not be very good, because Sc2 are not emerging from the region where incident beam is interacting on the specimen. They are emerging little away from where incident beam is striking to the specimen. Therefore, resolution will be not very good. On the other hand, if we look for ion microscope, helium ion microscope, then again we have same type of interaction volume, but this area is certainly smaller compared to the electrons, and when incident ion is falling on the specimen, then more Sc1s are generated. Why? More Sc1 will be generated. The ions will come and interact, and they will lose energy, and they have less chance to come out. Recoil will be more. As less chance to come out, certainly back scattered ion yield is also be less. As back scattered ion will be less, similarly the electrons which will come out from here, when a back scattered ion come out, from the specimen, that is what we are designated as back scattered ion. Here Sc2 will also be less. When Sc2 will be less and Sc1 is more, then we have a better resolution, because Sc1 is coming from the region where the incident ion or incident electrons is falling on the sample. So, in case of helium ion microscope or ion microscope, Sc1 is greater than Sc2 yield wise in helium ion microscope. In SCM, we have Sc2 yield is greater than Sc1 yield. This is about yield, and this is what we have see here. Sc1 come out, and this one are Sc2. So, this is the difference. Now, if we look at the graph signal level, as you see, this is for yield of secondary electrons and ion induced secondary electrons. This is for with helium ion microscope, how the energy spectra look like for in the range of 0 to 50. This is our secondary electrons generation range. For silicon, we see more ISE in ion induced secondary electrons are generating, and with a smaller energy width, narrow distribution of secondary electrons, smaller energy and also narrow distribution as compared to the SE generated from the electron being incident on the specimen. And in case of electron being incident on the specimen, this SE2 is quite large, that therefore, it is making it quite broad. But on the other hand, in case of ISI, absence of backscattered electron, or it is rather than say backscattered ion, not electron contribution, absence of backscattered ion contribution for ion induced SE2. This will be SE2 now, those which will be coming from here, from backscattered ion contribution. So, this is the difference, and therefore, helium ion microscope give much superior resolution as compared to the scanning electron microscope. Initially, we have seen in case of helium ion microscope, the wavelength is much smaller, therefore, we can get much smaller spot size. In addition to that, much less diffraction, and those are two another important reason for with helium ion microscope that gives the superior resolution, surface resolution. And in addition, we have seen here that how secondary electrons are generating just near where the incident ion is interacting on the specimen. And now, if we talk about the how the ion induced secondary electron generated, the mechanism of secondary electrons generation by using incident electrons is straightforward. On the other hand, in case of ion induced generation of secondary electrons, that follows 3 steps. The first step is there is a instant energy transfer from primary ions to the particles, that is electrons, in the specimen, any point in the specimen. First, energy transfer from primary ions, that is incidenting on the specimen, to the electrons inside the specimen. First, that will happen, energy transfer will happen, and then transport of once secondary electrons are generated inside the specimen, those secondary electrons should come to the surface, and then third step is they should come out of the surface, they should emerge from this from the surface of the specimen, then we can detect it. 3 steps. First step is generation of the electron, that is energy transfer from primary ion to the electrons. Second step is that electrons which are generated inside the specimen, they will be moving through the specimen to the surface, and then from surface they have to come out. Now, the second step and third steps is material dependent. Like in the second step, electrons being generated, and that secondary electron has to transport through the solid, through the material onto the surface. That depends on the electron diffusion inside the specimen, because that electron has to diffuse through the materials to reach the surface. So, it also will be dependent on the mean free path of the electrons in that specimen or in that material. The second step, that is transport of excited electrons to the surface. Then third step is that escape through the material. So, once it reaches to the surface, that has to come out of the surface, then only we can detect it. Now, it will depends on the work function of that specimen or material. Smaller the work function, easily they will come out. If larger the work function, it will take little difficulty to come out from the specimen. So, the third step, their escape through the surface barrier, nothing but work function, this also material dependent. So, this second and third step depend on the material, but let us look at the first step. So, an instant energy transfer from primary particle to the electrons, this is a multi-step process. This is a multi-step process, and it induced many channels. The first things that is this an important difference between the electron induced and ion induced generation of secondary electrons is that ion induced generation take 2 different forms. One is potential electron emission, and second one is kinetic electron emission. We will discuss these 2 emission process through which secondary electrons are generated when primary ion beams incident on the specimen. First is potential electron emission. Potential electron emission occurs when the incident ions interact with the specimen and then get neutralized, because it was an ion. If it takes an electron from the specimen, it will get neutralized, and once it takes an electron from this specimen and get neutralized, it will produce potential energy, and when it produces the potential energy, then that energy can be utilized to take out an electron from the specimen. That is a Ojai process. The first step is the neutralization, that means the ions get neutralized by taking an electron from the specimen, and that occurs through a tunneling mechanism. The electrons will tunnel to the ion to make it neutralized, and then it will release the potential energy, and once it releases the potential energy, that potential energy will be utilized to take out an electron from the specimen surface. This is a Ojai process, and in this way a secondary electron is emitted from the surface. And now the kinetic energy of this electron which is emitted depends on the kinetic energy of that electron will depends on ionization potential I minus 2 phi, where phi is the work function, So, kinetic energy of the secondary electrons which is emitted is equal to I ionization potential minus 2 phi. Now, ionization potential of helium is around 24.5 electron volt, and in most of the cases, the material cases, the phi work function is less than 10 electron volt. Therefore, in helium ion microscopy cases, the emission of secondary electrons undergoes a potential electron emission process, and then whatever the kinetic energy, that will be kinetic energy of these secondary electrons. This is the potential electron emission process. This is one. So, it first process is the tunneling of the electron from the ion solid to the ion, and second is energy transfer to another electron via Ojai process. This is what called potential electron emission. Now, second one is kinetic electron emission process. So, second one is when the kinetic energy of the incident ion is quite high, and it can penetrate deeper into the specimen. Once it penetrates deeper into the specimen or to a certain depth into the specimen, then it can lead to formation of a secondary electrons by various process. Those are like direct binary ion electron collision, it can happens. Second is it can be cascade of electron generation, as you see in the second cases. This is the direct binary ion electron collision. Second is the first secondary electrons are generated, and that electrons interacting with other produce two more electron like cascade of electron generation, and one will come out from the specimen. And third is electron generation through excitation by recoil of atoms, that will be recoiling through the atoms will go inside and interact with the specimen and produce secondary electrons. And fourth one is plasmon excitation. Plasmon excitation occurs also through potential electron emission. What is plasmon excitation? It means that when a ion is incidenting on the specimen, then that ions get first neutralized. Once it get neutralized, that means it takes an electron from the specimen. It takes an electron from the specimen, and now as it takes an electron from the specimen, it will produce a hole. So, once a hole is produced inside the specimen, that hole will be surrounded by many electrons, and those electrons will try to shield this hole. And once it happens, many electrons try to shield this hole, that is electron gas oscillation will occur. Due to many electrons coming to shield that hole, electron oscillation occurs, and that produce plasmon excitation. And this way, when it happens, the oscillation produce an electron, that is the plasmon excitation. So, these are the four different ways that secondary electrons can be generated from the kinetic electron emission process. If we look at the ion generated secondary electrons yield, what we can see that ion generated secondary yield certainly will increase initially as we increase the incident energy for all materials, it is increasing and coming to a maximum value and then decreasing. So, but here another important point to note that here energy is at least 10 keV. So, we need to because the mass of the helium ion and this ions is quite higher. Therefore, taking a smaller acceleration voltage will not be enough for helium ions to strike the specimen and produce secondary electrons. So, minimum energy normally the helium ion microscopy is operated in a potential range of 25 to 30 keV, and like for scanning electron microscope we do from 100 electron volts to around 20 kilo electron volt. So, it reaches maximum, but what if we even operate let us say 30 kV we are operating, then also our yield of secondary electrons is quite good. In case of scanning electron microscope SEM, the yield of secondary electron for each incident electron beam is around 1 to 1.5 secondary electrons. For each incident electrons we could generate 1 to 1.5 secondary electrons, but for helium ion microscope yield of secondary electrons for one incident ion is like 3 to 8 number of secondary electrons can be generated. So, it in this case much higher, yield will be much higher. Therefore, we can use much smaller beam current and also much finer spot, therefore, giving it higher resolution. The magnitude of the secondary electrons is found to be almost always higher than the corresponding secondary electron yield even at low ion velocity, then becomes significantly larger certainly at higher velocity and much higher as compared to the electrons. If we compare the yield of secondary electrons, it is a very important. You see here that with helium or ion, the yield, this is red one, it is quite increasing as we go high compared to the electron beam cases here, The yield is much higher secondary, it is secondary electron, it is much higher with helium ions as compared to the electron beam. So, we will discuss further in our next lecture about different secondary yield and other consequences of this SE1 and SE2. So, today we stop here. Thank you.